There is no more perfect system than a circular one, and no better attempt at closed-loop design than building for human habitation off Earth. Gateway, Artemis, and the enduring success of the ISS show the limitlessness of human potential and innovation in space, and highlight the importance of efficiency, reusability, and circularity in systems design. Amidst the excitement and opportunity of new space ventures, though, a less optimistic reality looms. Overproduction and waste, though inefficient, have become the global norm. Oil-based plastic pollution and organic waste generation and landfilling are huge drivers of climate change. But luckily today, we have a solution to both global crises with one new technology. My name is Delane Mayer, and I work with Full Cycle Bioplastics, a California-based biotech company whose patented IP turns organic waste into a non-toxic, compostable plastic alternative called Polyhydroxyalkanoate, or PHA. PHA-based plastic is fully customizable to its intended application, and it degrades harmlessly in a natural environment if not upcycled into virgin resin. Unlike other bioplastics, which rely on food source feedstock as a critical input, Full Cycle sources waste which would otherwise be landfilled, thus reducing methane and carbon emissions. Because of our feedstock sourcing, our PHA is the lowest cost, lowest carbon alternative to oil-based plastics and has the potential for widespread adoption, disrupting the trillion-dollar plastics market. Today, we work with some of the biggest food manufacturers to replace the plastic in their supply chains with food waste from their facilities. We're at TRL Level 8 thanks to successful commercial demonstration at our Tech Partners facility in Mountain View, and will advance to TRL 9 by 2022 as we commission our first licensed facility in New Zealand and a commercial scale facility in California. One of the larger PHA producers in the market expects to be sold out of PHA through 2024, so we're scaling up to meet this global demand. We expect to close our Series A round by the end of this quarter, and investment and project finance opportunities are available to scale this technology up on Earth. Beyond Earth, PHA's tailorability to use specification and end-of-life target makes it a unique and valuable material in space. PHA has the potential to enable circular product development, such as PHA-based 3D printer filaments, PHA protective padding for sensitive equipment to survive launch, or replacing LLDPE food packaging with seed-laden PHA-based packaging that could be planted in a space garden after use. Our technology could even be designed to transform human refuse into a PHA-based material for radiation shielding or construction. In space, we're learning circularity is a requirement for surviving off Earth. We believe it's a requirement for surviving here too.
I had a question for Full Cycle Bioplastics. You had mentioned that you're at TRL 8. Can you walk me through the commercialization steps for the next 18 to 24 months?
Sure. I'll actually turn that question over to Dane Anderson, who is our co-founder and co-CEO.
Thanks, Delane. So we're actively scaling up. We have a tiered scale into commercialization in our New Zealand facility, which is under design now. That first tier is a 10x scale up. And it's testing out a few modules at that size, and then we're scaling into additional scale-up modules and accepting new feedstocks in those in that facility. So we're essentially bringing in additional more concentrated carbon-rich feedstocks that will enable us to expand that facility and scale up the individual modules to a larger scale. And then in our California scale-up path, we're testing additional feedstock front-end sort of upstream systems there. And starting at a smaller module there as well. So we're actively engineering those scale-up facilities now and have signed the license for the New Zealand facility.
And from a revenue standpoint, so you will be revenue generating in 2021?
I mean, we are revenue generating through the license that we've signed, yes, but we don't expect that facility to produce material in a commissioned state until probably mid 2022. And that will be the recurring revenue off of the plastic production.
All right, and then I had one other question, and it's for Delane. And full cycle bioplastics. I was, you had briefly mentioned that, you could potentially take some of the packaging and eventually use it to maybe be used for plants or a seed bed to grow something on space. How easy would it be to convert the packaging you've created back into other products or other uses?
Yeah, that's a great question. So that's ideally how our PHA ends up, is we are upcycling it in a full cycle facility. So obviously, if we're doing that in space, we have another question about how we do anaerobic digestion on the ISS or on a lunar station. But on Earth, that is the intended end of life application.
It's very interesting. Those are all my questions, and I thank you.
And great job, everyone. Appreciate the presentations and hard work that went into it. My first question's for a full cycle. We talked about commercial scaling up. I'm thinking the other direction. So how well does your technology and methodology scale to local residential, or from a NASA perspective, a lunar habitat with 4 to 6 astronauts for 6 months to a year?
That's a very unique question. I would say, commercially, it might not be viable for us to pursue something at that scale. However, we're happy to work with NASA in any capacity. So if you want to talk offline, I would imagine it really comes down to the amount of feedstock that we're able to run through our system. And maybe, Dane, you have a better answer on what the minimum tonnage would be needed to set up a small facility.
Well, the economies of scale on 4 to 6 people are not great, Chris, but that's okay. Typically, we think a profitable, investable facility looks like able to serve about 40,000 to 50,000 people. So areas that small, which is not that much organic waste. I mean, we can take in sort of 150 to 200 tons a day and have that facility be standalone profitable with no subsidy whatsoever. So it allows us to distribute very small in terms of plastics production facilities, but in terms of individual household items, we haven't quite gotten the economics to function there. But I guess it depends on your appetite for expensive biopolymers in space.
Oh, perfect. I appreciate that. I look forward to the day where we have 40 or 50,000 people on the moon. So we'll see what comes of it.
Yeah, so I'm going to follow up to Chris and go back to full cycle with Delane. So talking about downscaling, if we're in a confined environment going out to the moon, how much can you automate this process? Is there hazardous byproducts that you can control if you had it in a smaller package?
That's a good question. I don't believe that there are any hazardous byproducts as a part of the process. I'll turn that over to Dane just to confirm.
Yeah, absolutely. No, there are no hazardous byproducts. I mean, we sort of stockpile the organic waste breakdown products into water solubles and don't let them come off as flammable gases. So there's no combustion risk. And even in the extraction process, we're able to use bioprocesses to purify the polymer. So it's a benign process.
You think there's a way to get to automating it, or does it have to be very hands-on when you do it here in the large scale?
I think as we develop more automation on the analytics to ensure quality, then yes. But right now there are still offline analyzers that require technicians and whatnot to push forward. But we are developing those currently. So I think yes, we will be able to get it to automate it.
And maybe flipping to the product side, when you've extracted the feedstock coming in, can we use that feedstock on a manufacturing environment? Have you looked at, if we use something like your product in a packing situation, any testing on that extracted material for how it handles in pressure and vacuum type environments?
We have not pursued the processing in vacuum environments yet, but we would be open to.
Thank you.
And then I have a question for Delane and Dane for you guys. Either one can take it. The recycling technology and the kind of full cycle concept is very popular, very hot right now. There's a huge number of players within the space. How do you differentiate yourselves, and how do you make yourself come up above the fray? Because there's a lot of people trying to do what you're doing right now.
Yeah, so one of the biggest differentiators is that we can take a mixed feedstock. So we are taking compost from, a municipal facility. It doesn't have to be perfect. It doesn't have to be pure. And we can take that mixed feedstock and turn it into a homogeneous VFA, volatile fatty acid intermediate. So that's one of the main differentiators. We're not, again, similar to what I said in the pitch, we're not using that food source feedstock, which has its own set of environmental and economic challenges behind that. And additionally, our PHA resin is made with wild and non-GMO bacteria. So our process is inherently more biodegradable because of those inputs. And Dane, feel free to chime in if I missed anything.
Yeah, sorry, just unmuting. Yeah, I think there are a bunch of players in the space for PHA, but there are different pathways and approaches. I think some of the other pathways that you may have seen are from methane. I believe Materials, New Light Technologies, they also pursue that. They both pursue methane-based pathways or gas-based pathways. We're able to essentially take that organic waste and not break it all the way down and not lose conversions on doing that, which also gives us more carbon access from the substrate. And we were able to build back up from those higher chain molecules or higher carbon number molecules into the PHBV that we make. And beyond that, the PHBV is a tailorable comonomer. It's much more, and has many more options to replace polypropylene, polystyrene, and polyethylene, depending on that comonomer composition. And because we go from those volatile acids, we have access to any of those comonomer compositions without paying for expensive precursors.
And then finally, for full cycle bioplastics, I'm just curious about if you've done any testing of your product material across extreme environments and temperature changes. Do you know anything about how its performance is based on the raw materials you're using to produce the plastics?
Thanks for the question. I'll turn that one over to Dane as well.
Yeah, great question. Extreme is a relative term, I guess. Most of the it's a fermentation-derived process, so we need to be at reasonable mesophilic temperatures to generate the polymer. But the polymer, once it's produced and how it behaves in various temperatures, bioplastics for the most part have lower melting points, so I wouldn't shield the outside of a spacecraft with it. It's behaved well in my stomach. I ate some and it went fine for me. But it does not have a great mouthfeel. It's very plasticky. That's a long way to say we've not done too extreme temperature testing on the polymers itself. It has a TG around 0 for glass transition temperature. So you may start to see some changes as it gets to very low temperatures.
I'd like to, first of all, thank everybody who participated. Not just, especially, our judges. There's so many people who came and did a great job here. Our judges, our collaborators at Synapse and Tampa Bay Wave. All the innovators who came. I know it's challenging to do videos and you're probably used to pitches and going into the virtual environment. It's tough, and I really appreciate all the work that you guys did and all the judges. The judging was very difficult. We had to make a tough decision. But we did finally reach a decision, and I will give you just a little bit of, this is my personal thoughts to frame the decision. I've always been kind of embarrassed as an NASA employee when I think about space garbage. I thought that as, landfilling the world is something that I think is embarrassing for us as human beings. But I thought, hey, once we're engineers, we're NASA, we go into space, we can be better than this, right? And then we go up into low Earth orbit, we got junk flying all around, and it's embarrassing. And I personally love the idea that as we go out into onto lunar or Martian applications, or just living in space in general, that we are forced by necessity to really make everything cyclical, to deal with your waste stream in a way that is that makes it so you don't have to launch as much, but also forces you to be a better steward of your environment, because your environment is very just scarce when you're in space. And for that reason, we decided to go with full cycle bioplastics as the winner for Ignite the Night.
I accept. Thank you. No, it's an incredible honor. It's very humbling to have even been able to participate. So thank you all so much. Obviously, we are here because the space biomanufacturing potential is really awesome. But Full Cycle really exists to address the climate crisis from multiple angles. We know that if we can get off Earth, for some of us, that seems like a good solution. But while we're stuck here, we really need to deal with the carbon and methane in the atmosphere and come up with more viable solutions. And, you know, personally, I'm a big believer that Full Cycle and PHA, the way we do it, is that solution. So thank you all so much for the opportunity. For anyone who's interested in seeing if your feedstock is viable in our process, if you're interested in licensing our technology, my email is Delane@fullcyclebioplastics.com, and I would love to talk to you. Thank you all. Really appreciate it.